Hello, this is a continuation of my series about artificial intelligence, and in this video, we're going to be talking about problem solving and how it's used to solve some problems that are related to artificial intelligence. We will be demonstrating over here the concept of problem solving and problem reduction. Okay, so we'll be talking about problem solving, and we're talking about symbolic integration. So we will take the symbolic integration as an example, and then we'll show you how we can actually make a goal tree using this symbolic integration problem. So let's start by first defining what is problem reduction. So in problem reduction, we will be using the generate and test methodology. If you want to know more about the generate and test, please go down to the description below and you will find a link to my previous lecture in which I talk about the generate and test. You can view that over there and then come back to this video. So we're going to be using the generate and test methodology. We will try different things. Basically, in the generate and test, we try different things and hope that we can get the answer to our question. So what we're going to do is we're going to take an integration problem. We're going to take a difficult integration problem and we'll attempt to solve it, and we'll see how we can use something called problem reduction. Now, what is problem reduction? Problem reduction is a method in which you take a complex problem, as is shown over here. For example, in this picture, you have a complex problem, complex machinery over here, and you want to divide it into smaller sets of problems that you can actually solve. So you have a big problem, and to solve this problem, what you try to do is you try to reduce the problems to a smaller size so that you can actually have a solution for that problem. What we will do is for each state or step of the problem, we will denote it as a node, and we will show it uh, as a node so that we can actually represent the problem in nodes, and then we can link the problems together. So we will have a big problem and then we will try to reduce it down. Okay, so the concept of problem reduction is basically pretty simple. Once you have a problem and that problem is complex, try to look for a solution that is simpler related to this problem, and then shrink that problem down until you get to a problem that you can actually solve, and then you can go ahead and get the solution of your problem. The example of this, for example, is a car. If you want to design a car is a complex system that might have electrical system in it. It might have an engine, it might have transmissions, the wheels, and the body of the car. There are many systems in it. So you break down the problem of the car into these problems. Now each problem might be divided into sub-problems, and you can divide them until you reach to a problem that you can actually solve. Once you solve all the problems, you can actually combine all of this together and at the end get yourself a car by integrating all of these small solutions with each other. So this is the concept of problem solving using problem reduction. So we're going to be using the same idea into the integration problem. And let's go to the integration problem. Before we go to the integration problem, let's talk about problem reduction. In the problem reduction, sometimes we have to divide the complex problem into sets of problems that we have to solve. When we solve all of them, we can find the solution of the problem that we have. So for example, you might have a problem where you have in a state of S1 and you reduced it to a state of S2. Now when you try to reduce it from the state of S2, you get to three different problems that you have to solve. If you solve all three problems, you can actually solve S2. Now how can this be visualized? So let's take an example over here. Let's take an example that we have an integration of x squared plus let's take 3x plus 1, and the whole thing is integrated with dx. Okay, we want to solve this problem. Now this is not a very complicated problem, but it's fairly complicated, and we can simplify this problem. We can simplify this problem into the integration of x squared dx, and then we can add to it 3 integration of x dx, and then we can add to it the integration of dx. Okay, so this is basically the big problem that we have, and we have broken down this problem into 3 sets of problem. Now these 3 sets of problem, we have to solve all of them to get the solution, and that is why we usually put something like this over here indicating that is all have to be solved so that we can actually get the solution of our first problem. So our first problem is generated to A, B, and C. So we have A, B, C problems. If we solve A, B, C problem and we put them together, we get the solution of our problem. Now this is called what we call the AND node. Okay, so this is going to be the AND node. So we're going to have a node over here, and then it's going to be having three different solutions, and these will be the ABCs over here. So you have the A, the B, and the C, and this is the one over here, and we will put this line to indicate that you have to solve all of the problem. The line looks like this letter looks like an A, and this is how I know this is an AND node. So a little bit of trick over here to actually have the AND nodes for you. So these are my three states that I have to solve, and this basically indicates that whenever I have an AND node, I have to solve all of the problems to be able to solve my original problem. Okay, so this is what an AND node is, a very simple example for the AND node. Okay, so let's go back. Okay, so this is the AND node. Now let's talk about the OR node. So sometimes when you have a problem and you try to reduce it, you might reach to a state in which this problem can be solved in multiple ways. Okay, you can choose any way of solving it. So this problem can be reduced to this problem, or it can be reduced to this problem, or to any other third problem. You do not have to solve all of them. It's only one of them that you have to solve. If you solve that one, then that's it. You got the solution of your problem. This is what we call an OR node. In the OR node, we have to pick which problem to solve. And as human beings, we like to solve the easiest problem. And we have to do that in the artificial intelligence in a way that we can actually tell the computer to do it. So we are going to have to tell the computer which problem to solve if we reach an OR node, because the computer needs a set of instructions to tell it which one is the easiest and how are we going to solve it. And we'll be talking about this more when we come to the example of the integration. We will see a clear example of an OR node and an AND node, and you can actually comprehend how the problem reduction is basically working. So we have two types of node. We have an AND node and an OR node. All of them branch. In the AND node, I have to solve all the problems in the AND node to solve the problem that I have in hand. In the OR node, I have to pick one and I can solve that problem. So let's go to the integration problem now. Now I am actually choosing over here a fairly difficult problem over here. So this is a problem. So integration of minus 5 x to the power 4 divided by 1 minus x squared to the power of 5 over 2 dx. This is a fairly complex problem. If you'd like, you can actually pause the video over here and you can actually try to attempt this on a piece of paper and try to find the solution. Now I'll caution you that the solution is not is easy. It's not done in 1-2 steps. You'll have to do a few steps to get this integration. And what we want to do, we want the computer basically to solve this. So to be able to solve this by a computer, first we have to solve it. So if we solve it, we can actually tell the computer how to solve it. The computer will follow the steps and he will solve the integration problem. So for the integration problem, we have to start with things that we know. Okay, so in the symbolic integration, for example, we know we have this table, and this table we call it the table that I have all the integration and the table of solutions. Basically, I have 1 over x dx. If I have the integration of this, I know that the integration is ln of x. Okay, so this is the solution. So if I reach to this state, I know this is my solution. And then I have the x to the power of n dx. This is the solution for it. If I reach to a state where I have x to the n, I can actually integrate that. And the integration of cosine x is equal to the sine of x. So this is the table of solution that I have. I have these three equations in my table of solution. And my computer, if it reaches one of these, it actually can solve the integration problem. So my task then becomes taking this integration problem and simplifying it until I reach these states. If I reach these states or these goals, I can actually solve my problem. So you see how we actually are trying to divide the problem into simpler problems. So unfortunately, the equation that I have over here is not in the form of 1 over x or x to the power n or cosine x, and hence I cannot actually get the solution of this because in the table of solution, I do not have the solution of this. So what are we going to do? Now the question becomes over here is that if a program can actually solve this, will it be called an intelligent program? I leave that question for you to answer. You can answer it after you see the video. So we're starting with something that are facts in the integration world. So we'll start with the safe transform. And a safe transform is a transform that you can apply anytime, and that will result in reduction of the problem, okay? So it's a very safe transform. You can always apply it if you can apply it onto the integration. If it applies, you can use it to reduce the problem. What is the first one is the sign rule, where if you have the integration of minus f of x dx, you can actually take this sign out, so it will become minus the integration of f of x. So now you can actually take the sign out and concentrate on the f of x, get the integration of the f of x, and once you get the integration of f of x, you just have to negate a sign, and you got yourself your integration. So this is a pretty safe transform, and you can use it whenever you face it, and you will have no issues. It will always work, and it will always reduce your problem. The second safe transform that you have is the constant rule. So if you have a constant, just like C over here, okay, so if you have a constant over here, C, actually you can take it out of the integration, and you can have the integration of fx. That's basically another safe transform that you can do. The third one is the integration of the sum of f of x's dx is equal to the sum of the integration of f of x's dx. Basically, you can actually take the integration inside the summation, and that's what we did in the previously in a few seconds ago with the slides that I actually typed x squared plus 3x plus 1, and we integrated and we divided it into 3, and we were explaining the entry. This is basically a safe transform that you can always apply without any problem in any integration problem. The fourth safe transform that you have is if you have the integration of px over gx, where the degree of px is higher than the degree of gx, then you basically do long division, and that is guaranteed to give you a simpler problem. Okay, so these are the safe transforms, and we can actually apply these safe transforms whenever we want, however we want them, if it applies. So if I have an integration that has a minus sign, I can use rule 1. If I have a constant, I can use rule 2. If I have this integration of the sums, I can turn it into the sum of integrations using the sum rule. And if I have px greater than gx, I can use the division rule, and that will simplify my problem. Okay, so these are called the safe transforms. Now we turn to something called the heuristic transform. What are the heuristic transforms? Heuristic transforms are transforms that are not safe. What do we mean are not safe? If we apply this heuristic transform, we do not know if the problem will be reduced or will it explode and become more difficult, okay? It will become more complicated. So that's the problem with heuristic transform. It is not always the case that when you use them, you get a simpler result. You might get a more complicated result. So the task becomes then choosing a heuristic transform that will help in reducing the problem. Now, what are the heuristic transforms that we have? We have the trigonometric functions. So if you have a function of sine x, cosine x, tan x, cotan x, secant of x, or cosecant of x, you can actually transform it into a function of sine x, cosine x, or a function of tan x and cosecant x. And you might have taken in the old math courses a cheat sheet that has all the trigonometric function in it. You can Google it and find it on the internet. So these are all the trigonometric functions that are there for us to use, and we are going to be using them. This is one of the transforms, the heuristic transforms. It might work, it might not work, it might simplify the problem, it might not simplify the problem, hence they are put in the heuristic transform. There is another transformation which is called the trigonometric to polynomial transformation. So if you have an integration where there's a function of tan of x, you can actually make it a function of y divided by 1 plus y squared dy. So this is basically taking the trigonometric function and changing it into a polynomial type. So you have a polynomial here, and this sometimes makes the problem easier to solve because we are stuck. We do not know what the tan integration results with, so we can actually use it in a polynomial, and then we can proceed further. The third type of heuristic transform are polynomial trigonometric. These are two that I'm listing over here. 1 plus x squared is equal to the sine of y, and 1 plus x squared is equal to tan of y. These are two heuristic transforms that we can apply. If we apply them, we go from the polynomial form to the trigonometric form, and these are transforms that sometimes might work, sometimes they might complicate things. Okay, so we have to be very careful on what we are going to select in the heuristic transform so that our problem is actually reduced. So given all of these, let's start the integration process. So how are we going to be looking at the integration? So we'll use something called the generate and test methodology. And in the generate and test methodology, what we will do, number one, we will apply a safe transform. We will look at our equation that we have, and we'll look for a safe transform that we can apply on it. If we can't, we are going to apply it because that is guaranteed to reduce my problem. After I apply the safe transform, I'm going to go to step 2, where I'm going to look for in the table of solutions, do I have that solution? Do I have that equation in the solution? If I have that, I'm done. If I don't have that, I go down over here to step 3 and I find a problem to work on. So I look for a problem to actually work on. How am I going to take this problem and tackle it? So I look at the heuristic transforms and I apply in step number 4 one of the heuristic transform that will result for me with a problem reduction. Okay. After I do this, I go back to the safe and then do any safe transforms that are there, and then I look in the table of solution and I keep doing this. I go in loops in this. I keep doing this until I find my solution in the table of solution, and when I find the table of solution, I am basically done. Okay, so this is the general methodology that we're going to be talking about. This is called the generate and test. We are using that, so we're going to be going and generating lots of heuristic transforms and safe transforms until we reach to our goal. Okay, so let's take the example. So first, the example that we have, I have minus 5x to the power 4 divided by this bracket to the power 5 over 2. As you can see, the minus over here is one of the safe transforms that I can do. So now this problem can be reduced to this problem. Notice I have taken the minus sign out. If I take the minus sign out, I only have to find the solution of this. Now notice this is not an equal sign, this is an arrow. So if I solve this, I can actually solve this. I just have to multiply it by negative 1 to get the solution. So this is now a problem that is reduced. I had a big problem and I took the sign and I made it a bit smaller, okay? Not very small, but a bit smaller. It became easier to tackle. The next heuristic transform that I have the 5 over here, I can take it out. So this problem reduces to this problem where I have x to the power 4 divided by 1 minus x squared to the power 5 over 2 dx. So I have used two safe transforms over here, and I have reduced this problem to this. Now everybody can see over here that this problem actually is simpler than this problem, okay? It's not very simple, but it is simpler in some sense from the original problem. And these are the list of transforms that I have used over here. You can go over them and try them by yourself if you are interested. So we have made it to a simpler form, but this form is still not in our table of solutions. So what are we going to do? There are no more safe transforms that we can do, so we will have to go and pick one of the heuristic transforms. So the heuristic transform that we're going to pick is we're going to pick the x is equal to sine y, and then that makes the dx is equal to cosine y dy. We're going to take our problem, the reduced problem, and then we are going to apply this heuristic transform on it, and we're going to shift it to a trigonometric form. And when we apply this, we substitute for x sine x, and we get this equation, and for the dx to cosine y dy, we can actually simplify this because 1 minus sine square of y is basically cosine square. The cosine square to the power of 5 over 2 is cosine to the power of 5 because the 2 will cancel with the 2. And then we have a cosine y over here. This is going to cancel out, so we'll have a cosine to the power of 4 in the denominator, and the numerator will be sine to the power of 4y. So you can see this problem is much simpler than this problem, okay? And this is something that we can actually handle much better than this. So we have used a heuristic transform that actually simplified for me my problem. So this is now becoming easier. So we have reached to this level, and we have now to find a solution for this so that we can find the solution of our original problem. Now, is there any safe transform that we can apply? No, there is no safe transform, so let's look for another heuristic transform. Now, to get a heuristic transform for this, we have two heuristic transforms that we can apply. So the sine to the power of 4y divided by the cosine to the power of 4y basically can be transformed into a 1 over cotan y or to the tan y. So we can actually transfer this fraction that is over here to 1 over cotan y and to tan y. Now, which one are we going to be picking? Of course, we'll be picking the easiest, and the easiest looks like the tan of y. Why is the tan of y easier? We have tan of y, which is a difficult one, and a cotan of y, which looks as equivalent in difficulty as a tan of y maybe. But we have more operations over here. We have 1 over this, and we don't have the 1 over this. So we instruct the computer to basically take the tan of y. Okay? So because this is simpler, we're going to make our program take this and then leave this because this is actually simpler. So the sine to the 4 over the cosine to the 4y dy, we are going to transform it to the tan y. So we have the contenders, the 1 over cotan y and 1 over tan y, and the tan y wins. And we are going to be using the tan to actually replace our problem. So we are taking the tan. So now we have the integration of tan y dy. But the integration of tan y dy is also very complex, and I cannot solve it. So what do I have to do? I have to go to another heuristic transform, and I am going to be using the fact that integration of f of tan of x dx is equal to integration of f of y divided by 1 plus y squared dy, and I'm going to change from the trigonometric form back to the polynomial form. Okay, and if you do this and with some basic variable transformation, you can actually take the tan y dy and represent it using this integration. So it'll become the integration of z to the power of 4 divided by 1 plus z to the power of 2 dz. Okay, so now I have transformed the tan y. Now you might ask me a question over here and say, hey, we had sine to the power of 4 divided by cosine to the power of 4. How are you working with tan y dy where there was a 4? What I can say is, well, if you get the solution of the tan y dy, you just have to take it to the power of 4 and you got yourself your solution. So we can reduce the problem of taking the power of 4 out, and we can work only on the tan, and once we find the solution for that, we can take it to the power of 4 and we got our solution. So this is why we don't have the power of 4 in the tan, and we can actually now work with this. Now, is this problem easier than the tan of y? The answer is maybe not, okay? But our program over here has no choice. It has to go further because this problem, it is not in the solution table that we have, and it has to move forward, so it has to pick this to solve it, okay? So a bit more complication over here, but it's a route that we have to take. Now, we don't have any safe transforms to apply over here. Well, sorry, we do. So we have over z to the power of 4. This is the polynomial of order of 4, and we have another polynomial over here of power of 2. So we have px over gx. So the power over here is greater than the power here. I can actually do a long division. So if I do a long division for this, I can actually transform this into something like this. Okay, so it'll become z squared minus 1 plus 1 over 1 plus z squared dz. Now notice over here, I could not get rid of this this part, which is still a fraction part in my equation. But again, this is much simpler than this. And is there any safe transform that we can apply over here? Yes, this is the integration of sum of terms. So we have one term here, another term here, and another third term here. So what we could do is we can divide this problem into three sets of problems. So this problem, we can have the z squared on its own. So I can get the integration of z squared dx or dz, and I can get the integration of minus 1 dz. So the minus 1 dz is over here, and the third one, which is down here, is 1 over 1 plus z squared dz. Now, for the first term, okay, this is our and node. So we have to solve all of these three, basically. All of these three, we have to solve them to get the result of this integration. So the integration of z squared dz, hey, this is in my table. Okay, so I can actually do this in my solution table because this is a power of 2 of a variable, and I can get the solution. So I am done with this integration. In the minus 1 dz, I can apply a safe transform, take the minus out, and then I get the integration of dz. And the integration of dz again is in the table, so 1 over here is nothing but x to the power of 0. And the same rule that I use for here, I can actually use here, and I am done with the solution. So I am done with two terms, and let's look at the third term. Now the third term is still one of the difficult terms that we have. It's 1 over 1 plus z squared dz. So this is still not in my table, so not in my solution table. So I have to keep working on this problem until I find the solution for this. But for these two, I got the solution. So I'm not going to work on them anymore. I know the solution of these two now. So let's take the problem of 1 divided by 1 plus z squared dz. Now there is no safe transform that I can apply onto this. So the degree of the numerator is less than the degree of the denominator. I cannot do a long division. There is no sign. There is nothing. So I will be stuck, and I have to do another heuristic transform. What is the heuristic transform that I'm going to do? The heuristic transform that I'm going to do, I'm going to make z is equal to tan of w, or tan of omega, and then the dz will become 1 over cosine square omega d omega. And then the equation that I have is 1 over 1 plus z squared dz. When I substitute this into the equation and do some simplification, I get this result to be the integration of dw. Okay, the integration of dw is in my table. Okay, so I got the solution for this, and I can actually use this in the integration table. This is what I have. The solution is this. Just replace the x with the w to the power of 0, and will become 0, and you got yourself your solution. So we have actually solved all the problems. So now let's look at what is happening over here. Okay, so let's recap and let's take a summary of what happened. We started with this problem. We had the minus and we took it out, so we reduced the problem to become 5 to the power of 5x to the power of 4. Then we said, hey, the 5 is another safe transform that I have. I can take it out, so I reduced the problem to this. Then I did not have any safe transform, so what I did is I did a heuristic transform and transformed this to this, which eventually came out to be sine to the power of 4 divided by cosine to the power of 4. When I had this, I had the choice. Either I solve 1 over cotan x or I solve tan y dy. Now notice this is an OR junction, okay? So this node generates an OR junction. I can solve either this or this to get my solution. Based on the complexity, we took the tan, and then from the tan, we actually went over here and used another heuristic transform to transform it to this type of polynomial, okay? And then once the polynomial was there, we used the safe transform and we divided the numerator on the denominator, and from the long division, we got ourselves this form. Then we divided this into, using a safe transform, into 3 problems with an AND node. Okay, so this is a node that is having an AND branch with it, so you have to solve all of it, and hence the line over here. And the first problem that we have to solve is z squared dz. This is in my table of solutions, so that's done. Then I had the minus 1 dz. I took the safe transform, took the minus out, so it became the dz, and I have this in my table of solution. The last problem that I had in the AND node is 1 over 1 plus z squared dz, and we use the heuristic transform again to transform this, and we got it to be the integration of dw, and this is also in my table of solutions. So I got the solution for this, the solution for this, the solution for this. Now what I have to do is just backtrack, put the solution. I took the minus over here, so I multiply this by the minus. I add all of these together and keep on going back. Over here I have a tan, so I have a tan to the sines to the 4 and cosine 4, so I have to raise it to the power of 4, and I can backtrack and get the solution for my integration. So you apply all the safe transform that you did, you took the constants out, whatever you did, you have to go back and just track them, and the computer will be able to solve my problem. Okay, so this is how we can actually program a computer to solve the problem. So we only give it the heuristic transforms and the safe transforms and the table of solutions, and then the computer can actually then go and explore. So once it starts from this state, for example. Okay, so it starts from this state, and in this state, it's going to say, can I apply a safe transform? The answer is yes. It goes from this state to this state, then applies another safe transform, gets to yes, and comes to this state. Now going from here, there is no more safe transforms to apply, so it's going to apply one of the heuristic transforms. Now, which heuristic transform should it apply? Since it's a computer, we can ask it to use all heuristic transforms, apply them, and then try to reduce everything. Once you reduce everything, pick the one that has the least complexity, okay? And this will turn out to be the least complex one. And then we go on, when we do this, heuristic transform, we come out with this. This will be the least complex one that's coming out. The other heuristic transform are just going to complicate the problem, and the computer will not take those routes to actually solve those problems. It will take this problem because this is actually the simplest among, or the easiest one among the ones that he has. This then had two options to be solved. Now over here, what's going to do is going to take the tan, because it has less number of operations to basically be done, and it's going to expand it, and this is going to be the new thing that has to solve. Now I have to caution you, and then the computer program, when you reach to this, the computer, since it has this unexplored, it's going to try to the computer is going to shift from here. Instead of going down here, it's going to go over here, because it's going to say, hey, I have more operations over here than here. There's only division. This is division plus addition. So it's going to go explore this, and it's going to apply some heuristic transform on it. It's going to apply all the heuristic transforms. After it applies all the heuristic transforms, the expression that's going to come out, the simplest expression, is going to be very complicated, and it will revert back over here and try to solve this, okay? So the computer basically, in the tree that is generating, so this is basically generating a tree like a structure. You can actually pull this out, and you can see it's coming out like a tree. In all the leaves, it's going to try to attempt all type of heuristic transforms that it has, and then compare and do the one that has the simplest, okay, the least type of operation, or the thing that is actually having a solution in the table of solutions. So it actually will go from here, do the cotan, and do some calculation, get a term that is very complicated. I'm not showing it over here, and then come back and decide, oh, this is easier than this term, and then continues over here. And then when it comes over here, it says, oh, I have a safe transform, and it does this AND node, and then in the AND node, it basically, and in the AND node, basically, it finds the solution for the first term, the second term. It applies the safe transform and gets the solution here. And then for this, it has to do another heuristic transform. It will apply all heuristic transform. One of the heuristic transform will result with this, and then it has the solution, and it can get you the answer of your question. Okay, so this is how the computer actually works. Now, what I am doing over here is I am going to label these. So if I label this state to be A, and this state to be B, and this state to be C, and this is D going on. I label all of them with alphabets over here. Now you can see that I can actually transfer this problem that I have, the problem, this is my tree, so my tree is coming like this, and then it's coming over here, and then it's branching with an OR node, then it's coming over here, and then it's branching from here with an AND node, and then a 3 over here. As we go on, we can actually take this, okay, we can actually take this tree, you can spread it out, and what I'm going to do is I'm just going to represent each equation over here by the letter that I have given on top of it. And furthermore, if you have a white circle, that means I have applied a safe transform to get over here. If I have a yellow circle, I have applied a heuristic transform just to have a good visualization of what's happening. And I can actually make a tree that is coming like this. So this tree is basically copying the behavior of my integration program. So notice the A goes to the B, goes to C, goes to the D, goes to the E. This is exactly the same. A goes to B, goes to C, goes to D, goes to E, and then I have the branch with OR branch goes to F and G, and I have it over here, F and G. I did not explore F, so I'm not going to do anything with it. G, I have applied heuristic transforms, and you can see how I'm representing this as a tree. This is what we call a goal tree. So we started with a problem and we want to our goals. So our goals was to find an integration that is in my table of integration. So we actually were able to do that, and you can look at the tree, and the tree are one of the most powerful representations that can be representing a problem. And we human beings have lots of perception, and when we look at a tree we can get a lot of information from it. For example, there is something that's called the depth of the tree. The depth of the tree is how deep the tree is going. So if we leave the 3 safe transforms that are on the top out, the depth of the tree where we are using the heuristic transform is 1, 2, 3, 4, 5, 6, 7. So these are the heuristic transform. This is the depth. The depth is the worst case length of the tree that you have. Now you have two cases. One is like this one, and the other one is coming for the K and L. So you can go D, E, G, H, I, K, L, or D, E, G, H, I, M, N. So they have both have the same. So this is 1, 2, 3, 4, 5, 6, 7. This is a tree of depth 7. It's a very complicated problem. The bigger the tree becomes, the harder the problem it is. Now, just to give you a comparison, somebody who was in the second year of engineering, for example, or in school in science and engineering, a student can actually solve a maximum of the depth of 3 if you're applying a heuristic transform, okay? Maybe a PhD professor can actually solve something that is 5 in depth, okay? So the example that we have given you, most of the people will have difficulty in solving, and they will have to spend a bit more time to do it. However, when you give this to a computer and explores all the options that it has, it can actually come out to the solution pretty fast. Okay, so the non-colored nodes over here are the safe transform nodes, and the color nodes that are here are the heuristic transforms that we have actually applied in them. Okay, so a very complex problem that we are presenting, but we can actually take any problem and represent it as in a tree, just like what we did with the integration problem. We represent it in a tree, and then from the tree you notice that the tree over here is not expanding too much. So this is the nature of the problem that we give to students in schools. It doesn't branch too much, okay? Otherwise the student will get confused. So we like to keep the tree together with self, maybe 1 or 2 branches, not more, to test the student whether they understand the concept or not. So you can see that there are much more information in the tree than just looking at the integration problem and looking at the solution that is written on a piece of paper. So you can actually take all of that data and transfer it to a tree, and that will help you visualize what's going on, get you some sort of complexity on how complex this problem is, and also give you some idea on how you can actually tackle problems that are similar to this. Okay, so with this we come to the end of our video. I hope you enjoyed it, and I hope to see you next time on the other videos. Take care. Bye bye.